Okay, before we get to more examples, I just want to slow down and pause and let us go through each of the 5 components of the RATEY method, and just to make sure that we have everything down before we start graphing things. So what you need to know first is that before you can use the RATEY method, you must factor both the numerator and denominator and remove any common factors. The common factors tell you where any holes are located, and so just like the previous example, whenever we had x minus 3 cancel out, that represented a hole in the graph, and so that's got to be done first. Once you do that, you can jump into finding the information. So I'm going to give you a second here to pause and write in the information here for root, and then I'll just discuss real quick. Okay, so hopefully you had a chance to write that in on your notes. R is for root. This is just another way to say x-intercept, but it's really hard to make an acronym with the word x, and so we went with root instead. And so remember that roots come from the numerator equaling to 0 and solving. These are the x-intercepts of the graph. You're going to write your answer as an ordered pair, and then quite possibly the most important aspect of this particular slide is right here. Graphs must pass through all of the roots on the graph and cannot cross the x-axis anywhere else. And so just like on the previous example, when I drew the red graph and I said, well, this can't be it because now I'm going through the x-axis somewhere where there's not a root, we're going to use that a lot to determine where the graph needs to go. So that last bullet point is very important. Okay, the A in RATEY stands for asymptotes, and more specifically the vertical asymptotes. And so remember that those come from the denominator being set equal to 0 and solving for x. We're going to write our answers as equations of lines, meaning x equals a number. And graphically, these vertical asymptotes act as boundary lines. And so what that means is that the graph can come close to a vertical asymptote, but it will never cross a vertical asymptote. So they literally are acting as boundary lines. And one more thing that's important for vertical asymptotes, essentially the number of vertical asymptotes is one less than the number of sections of the graph that you will have. So for example, on the previous example that we worked, example 3, there was one vertical asymptote and we drew 2 different sections of that graph. If there were 3 vertical asymptotes, I don't think I've given you a problem that has 3 vertical asymptotes, but let's just say, for example, that I did. That means that there would be 4 different sections, for lack of a better word, to that particular graph. And so I'm going to pause the video here or just stop talking for a second to give you a chance to pause the video and write this into your notes so that you have it. And then we'll move on to the next letter. Okay, the T in RATEY stands for tangency and or togetherness. So technically that's 2 T's, but the RATEY method doesn't sound nearly as good as the RATEY method, so we just kept it to 1 T. But essentially what you're looking for here is either tangency at a root, which occurs whenever you have multiplicity. Remember what that word means. It means a squared or just basically an exponent that's bigger than 1 in the numerator is going to tell me about tangency. Now, what does it mean for there to be tangency? It means that the graph is going to be tangent to the x-axis, or the way that we've discussed that in the past is bouncing off of the x-axis or touching the x-axis and just bouncing back off. And so just the picture that you're looking for is right over here. And so again, this would be if there is a squared in the numerator. So if in the numerator I had x minus 3 squared over, something in the denominator, this would indicate that I have tangency at the root 3, 0, which you can see from the picture is what we have going on. Now, the other T in the RATEY method is for togetherness about the asymptote, and this is whenever you have a multiplicity on the bottom or in the denominator. And what togetherness means is that the graph comes together at that asymptote. And so what I mean by that is that you can see here on both sides of this asymptote, the graph is coming together, meaning it's going to positive infinity on both sides. You could also have the graph, just for example, go to negative infinity on both sides. Now, obviously you wouldn't have both at the same time, but either both sides would go up or both sides would go down. So maybe this will help. If I think about what does it mean for a graph to be not together, if I have a vertical asymptote here, it means that I'm going up on one side of the vertical asymptote and I'm going down on the other side, or vice versa. And so that's what not together looks like. And so hopefully that gives you a better picture of what togetherness looks like about an asymptote. And again, this happens whenever I have a squared on the bottom. So if that x minus 3 squared came on the bottom and then I just had some other stuff up in the numerator, then that would mean that this function has togetherness at the asymptote x is equal to 3, since that's the factor that has the squared on it. And I'm just going to go ahead and answer this question now because I know you're probably thinking it. Is it possible for a function to have both tangency and togetherness at the same time? And the answer to that question is yes, and I'm going to work an example a little bit later that has both of those going on at the same time. Okay, the E in RATEY stands for end behavior, and so remember earlier I said that this means either your horizontal asymptote or your slant asymptote. And so in order to find one of those, we use our acronym, Bobo, Botan, Eats, DC, and we are going to graph that horizontal asymptote for the ends of the graph only. And so what that means, and I'm probably just going to add a third bullet point here, and go ahead and pause the video at any point so that you can write this down. This third bullet point is I'm going to say that a graph can sometimes, not always, not never, but sometimes cross a horizontal asymptote. And so remember that we said for vertical asymptotes, you will never cross a vertical asymptote, that those truly do act as boundary lines for the graph, but not so for end behavior. For horizontal asymptotes, a graph can sometimes cross the horizontal asymptote, but what you do know is that at the ends of the graph, either on the left end or the right end, negative infinity or positive infinity on the x-axis, that the graph is going to approach that horizontal asymptote. But somewhere like around the origin, not at the ends, you might cross a vertical asymptote. That might happen sometimes. Not necessarily all the time, not necessarily never, but sometimes you may cross a horizontal asymptote. Okay, finally, the Y stands for y-intercept. This is probably the easiest of the 5 concepts to understand because all you have to do to get the y-intercept is to plug in 0 for x and then solve for y. And then one thing that I didn't type here is that we are going to write our answer in the form of an ordered pair. So 0 comma a number will be how we write the answer for the y-intercept. So real quick, pause the video, get that written in on your notes under y-intercept, and then we are ready to start working some examples.